very fast, something on numerical integration. And this numerical integration is sometimes called numerical quadrature. Numerical quadrature. And this is the process of evaluating a definite integral from a set of numerical values of the integrand, let's say f of x. And if it's applied to a function of a single variable, if to a function of a single variable, it is a quadrature. So as quadrature. So the process of evaluating, now sometimes it's possible that you can be able, in this one you've done it before, you can be able to work out, you can integrate a given integrand analytically, but there are some situations where it's like impossible that you can be able to find or integrate a given function from the analytical methods. So this one calls for the process of numerical integration. And then we are saying that if this function f of x is a single variable function, and then the process is applied for this single variable function, then we will be talking about it as a quadrature. So how does the process work? So the procedure is as follows, that the problem of numerical integration is solved by, firstly, approximating the integrand by a polynomial interpolation formula, and then integrating this expansion. Now, you approximate the integrand by a polynomial. Then once this one is done, and of course this one is done by an appropriate interpolation formula, then of course you integrate the expansion between the limits of integration. the limits of integration. So once this one happens, it will be like you will have divided the limits of integration at some given intervals. Then for you to work out the final value of that integral, you'll be required then to add up all of them so that you're able to obtain the integral for the entire range. So you will first have to approximate, you approximate the integrand by a polynomial with the help of an appropriate interpolation formula. Then once that one is done, you integrate then between the limits of integration, then you get to the value of that integrand by adding up all as you subdivide it, you add up all of them, then you are able to get the integral for the entire range. Now, like we have done before, when we were talking about the interpolation, we had two situations where the values were equidistant, or where we were talking about equidistant ordinates, and where they were not equidistant. So we are going to look at appropriate methods of this numerical integration based on the distance between successive points or the ordinates. So one thing that you're supposed to note here, again, very fast, is that a general quadrature for equidistant ordinates is known as Newton Cotes formula. If the points are equidistant, then we will be talking about the Newton's Cotes formula. And of course, Newton's Cotes formula again will depend on the number of points that we will consider, as we are going to see. Under this, we are going to have quite a number of sub-formulae based on the Newton's Cotes formula. And there are going to be around 4 or 5 of them, and we will look at each one of them. So allow me to start off with this Newton Cotes formula, the general one, before we go specifically to the sub-formulae which are derived from this Newton Cotes formula. But the main issue that you are supposed to understand is that this first case, what we are going to look at, and possibly I think this is the match that we are going to do in terms of numerical integration. We will consider a case where we have equidistant ordinates. So the Newton So as I've said, this is the general quadrature formula for equidistant ordinates. That's what is called the Newton-Cote formula. In this case, the integral is this one is approximated using the polynomial or a series of polynomials piecewise to the function or our segments of constant length. But this is the general quadrature formula for the case when the points or the ordinates are of the same length or the same spacing, or when they are equidistant from each other. So in this case, what basically happens is that we will have to integrate to approximate the integral, and in this case, we'll use the polynomial, the whole of it, or sometimes we could have a series of polynomials, and this will be applied piecewise to the function or data over segments of constant length. So then let's see how it goes. Now suppose we have, let's have this integral a to b of the function fx with respect to x, then be approximated to the integral of dx, where in this case, fn is a polynomial of degree n. It's a polynomial of degree n. And the function f of x is defined in the interval, the open interval a, b, for certain equidistant values of x. Say we have x naught, x1, x2, all the way to xn, by dividing b minus a into n equal parts, each of width h, and of course corresponding y, the yi's as y naught, y1 all the way to yn. So we have, this is the integral that we have. We are supposed to approximate the integral from a to b of that function f of x with respect to x. Then we are told that, okay, this one, the integral of the function f of x with respect to x, we approximate it to be the integral as in that equation 1. And we are defining this fn of x as a polynomial of degree n. Then we are like this function f of x be defined on that interval ab, of course, because that is where we have the limits of integration. Then for some equidistant values of x, x0, x1 up to xn, where b minus a is divided into n equal parts, each of which has got a width of h units. And therefore, if that be the case, then we'll be talking about an equidistant distribution of the ordinates. And then, of course, we have the corresponding y's as y0, y1, up by n. So we have this pictorially as what I'm going to show you shortly. So we can have this as our x and that as our y. We can have this as our y0, y1, and so on, up to y n minus 1. Then we have yn. Of course, here we have x0 is equals to a. Then we have x1 all the way xn minus 1 up to xn. That's what we have. And the xn, this is xn, and xn is equal to b, which is equal to x0 plus nh. That's what we have. So this is what I'm talking about. We are starting from the point x0 is equals to a, then we are subdividing each one of the sub-intervals between the respective points. That is from x0 to x1, the difference is h, all the way up to xn, which is our b now, because the limits of integration are between a and b. And then from the x0 minus x1 equal to h, we can have this one equal to what we have here, that our b, the upper limit now will be x0 plus nh, to justify again that the points are equidistant as you go on with the approximation of the integral. So then, this being the case, that we can proceed as follows again. Then we have the following, that integral now becomes, we start from x0 to x0 plus nh, then we have fn x dx. So we can have this as h 0 to n f x naught plus r h dr. This is if we take x to be equal to x naught plus RH, and if this be the case, then if x is equals to x naught plus RH, then the rate of change of x with respect to r will be dx is equals to h dr. What I mean is that if we have x, this is what we have, then of course dx dr will be equal to h, so that dx will be h dr, and this h we have here is the same h that comes out there. Then we have f of, now x is x naught plus rh, x naught plus rh, like the way we have defined it above. So then, that being the case, and we have the following, this will be equal to h. Now the approximation of what we have there, the integral from 0 to n, then we have y naught plus r plus r minus 1 over 2 factorial y naught plus r minus 1 r minus 2 over 3 factorial, the third difference. Starting from that, we should recall that in this case we have used the forward difference interpolating polynomial. Then here we have the r. Let's call this equation 2. And further, on integrating term by term, we have, or we get the following. We get the I will be equal to the integral from x naught to x naught plus nh fn. This is equal to nh. We have y naught plus n over 2, y naught plus n minus 2, sorry, 2n minus 3 over 12 y naught plus n minus 2 squared over 24, and so on. That's what we have. And what we have here is what is called, we can call this one 3. Let's see how it goes. This is how we are approximating the integral at that point. So if we assume that x is equals to x naught plus rh, so that dx is equals to h dr, then the first integral here becomes now h 0 to n f of x naught plus rh. So what we have here as f of x naught plus rh, this can be approximated by Newton's forward interpolating polynomial, something which we have done before, and that will give us what is under these curly brackets, y naught r, the first difference, forward difference, then r minus 1, 2 factorial, the second forward difference, and so on. Then we integrate that with respect to r. Again, when you look at equation 2, it's possible that we can be able to integrate this y naught. We integrate the r, the first difference, the second one, and so on. When we are able to do all this, then we come up with equation 3. Now, equation 3 is the Newton's Cotes formula in its general form. which a number of formulae can be derived by putting n is equals to 1, n is equals to 2, n is equals to 3, and so on. So now what we are going to do up to this point, this is the general Newton-Cortez formula. Now, something else is going to happen if we put n is equals to 1. If we put n is equals to 1, we will come up with another formula. If we put n is equals to 2, we get another formula. Like, for example, if n is equals to 1, we'll be talking about the trapezoidal rule, or what we shall call Newton-Cortez formula for n is equals to 1. If we put n is equals to 2, then we'll be talking about Simpson's 1/3 rule, or Newton-Cortez formula for n is equals to 2, and so on. So let's see straight away something about the trapezoidal rule. Or before that, then we should note this. Let me note something here. Question 3 is the Newton-Cortez in its general. In which a number of formula can be derived for n is equals to 1, 2, 3, and so on. Again, I need you to note this, that the closed of equation 3 are those in which those where those were the data points at the beginning and the end of its limits are known. When we talk about the closed form of the Newton-Cortez formula, closed form, this is a case where the data points at the beginning and at the end of its limits are known, but we also have another form, that is the open form, whereas open forms have limits that that extend beyond the range of the data. So if this be the case, when they are outside or beyond the range of the data, then it means for the purposes of evaluation, then this will require a little bit of what is called extrapolation. But we are not interested in that for now. So I've said equation 3, what we have derived up to the previous slide, if I can call it that, is the Newton-Cotes formula in its general form. General form, because we can be able to come up with other formulae for different values of n. So these are the particular cases that we have. Now we start off with the first one. The first one is what is called the trapezoidal rule. And this is Newton-Cotes formula for n is equals to 1. Let the curve pass through the sets of values. We can have x naught, y naught, x1, y1, and so on up to xn, yn as a straight line. So as a straight line, in that case, we are talking about a polynomial of degree 1. That's what it means. Let again f of x be tabulated for x is equals to a, x is equals to a plus h up to x is equals to a plus n minus 1 h, and finally up to x is equals to a plus n h is equals to b, respectively. Then in that case, we have the following, that our integral will be a to b f of x with respect to x, and this will be the same as the integral from a to a plus h plus the integral from a plus h to a plus 2h plus all the way to the integral a plus n minus 1 h up to a plus nh f of x with respect to x. So we are talking about these points. From the first integral will be from this point to that point to a plus h. Then of course from a plus h it will be the next one will be x is equals to a plus h, so which will be a plus h to a plus 2h, and so on up to that, the last point, that is b. Or we can have it as we can have it as I is equals to I plus I2 plus that plus IN. Is that okay up to that point? I proceed.
Yes, it's okay.
All right. So if we can, if we put x to be equal to a plus RH, so that the R is equals to H, sorry, the X is equals to H dr, and of course we have the limits as X is equals to R, to X is equals to A plus H, and of course R in this case is equals to 1. We then have the integral A plus H f of x dx. This will be equal to the integral 0 to 1 A plus RH dr. And by Newton's forward difference, formula, which we can easily state here, that is F A plus RH, this will be equal to plus R plus R minus 1 over 2 factorial, the second difference of that, plus and so on. Let's call that equation 2. We will have the first, we will have I1 will be equal to the integral A plus H, and this will be equal to H, the integral 0 to 1 y naught plus the first difference R minus 1 over 2 factorial, the second difference plus R minus 1, R minus 2 over 3 factorial, the third difference, and so on. And of course, the whole of that, we find it with respect to R. Let's call that one 3. So what we have here then will be equal to this will be equal to, we have it as H, or can I have it at this point? So this is equal to H y naught plus a half y1 minus y naught plus 0 plus 0 plus 0 and so on.
Excuse me, sir.
Yes?
You're not seeing
Yes?
at the lower part. You know, the lower part is not visible.
Okay. Then up to equation 3, you are able to see that?
Yes.
Perfect. Then we move to the next one. So that will be the same as or, we can say or I1 is equals to H y naught plus a half y1 minus y naught plus 0 and so on. Now, this is the case because the curve passing through the points x0, x1 up to yn is a polynomial of first degree. And therefore, the differences of order higher than the first one vanishes. So that's why we have these zeros. So you can note this. This is because the curve passing through the points x0, x1, and so on is a polynomial of first degree, and hence of order higher than first vanishes. That is why we have all these zeros. We go up to the first difference, then the rest will be just zeros. And therefore, then, in that case, we have the following. We have it that I1 is equals to H, Y0 plus a half Y1, Y0. And this will be equal to H over 2 Y0 minus Y1. And then we can have the second one. This will be equal to, again, the integral x0 plus h to x0 plus 2h f and x dx. And this will be, again, h over 2 y1 plus, this plus, not minus, plus y2, because when you open these brackets, this will be half y1 and then y1, a half y1 minus a half y0. So y0 minus a half y0 is a half y0. So it's y0 plus y1. So this will be y1 plus y2. This can continue the same way up to when we have, so you can note it down here again. So this one continues like that. So up to this point, I think it's okay, because from here, you've understood why the rest of this is going to 0, because we are talking about this, these data points will have to go up to the first degree. So we know, in fact, the difference is higher than the first difference will be zeros. So that's why we are able to get the first integral as h over 2 y0 plus y1. And in the same way, the second sub-integral, again, will be h over 2, now y1 plus y2. Remember the figure that we drew before. So we are now talking about the y's, y1, y2, y3, and so on, up to yn. So then in that case, we can have the last one, we have that way. Then we have that will be the integral from x0 plus n minus 1 x0 plus nh, that is b now, that's f dx, and this will be equal to h over 2. We have y n minus 1 plus yn. So the whole of that, we can have it as equation 4. So adding them, we get, so we have I, which is I1 plus I2, and so on. So this will be equal to H over 2. We have Y naught plus Yn, then plus twice Y1 plus Y2 plus Y3 and plus Yn minus 1. This equation 5 is the trapezoidal formula or Newton-Cotes formula for n is equals to 1. So I hope you are seeing how we are coming up with equation 5, sorry, because if you look at this, we are summing them up. So look at this one. If we have this as our I1 as H over 2, Y naught plus Y1, then I2 as H over 2, Y1 plus Y2, I could then say I3 will be H over 2, Y2 plus Y3. Is that correct? Are we together there?
Yes.
So if we are adding, that's what I wanted to show you is that why does it come out that for equation 5, we have some have a half and others are full. So if we are adding, for example, I1 plus I2 plus say I3, we will have H over 2 Y naught plus H over 2 Y1 plus H over 2 Y1 plus H over 2 Y2 plus H over 2 Y2 plus H over 2 Y3. So, sorry, this is H over 2. So you look at this, if we go up to 3, for Y naught, we only have H over 2. But for Y1, H over 2, so this will be H Y1, correct? And then for H over 2, Y2, this and that, again, we have H Y2. But now for the last one, again, it will have H over 2. Unless we go to I4, which will be plus H over 2 Y3 plus H over 2 Y4 and so on. So that's why then in that case, when we sum up the individual integrals, we come up with, so we have it here. We have it that there is this H over 2, but now for Y1, the Y naught and Yn will have H over 2, but the Y1, Y2 up to Yn minus 1, if you multiply this one out, this will cancel, this will have H. This will have H over 2, and this will have H at the end of it all. That's why I have it like that. So this equation 5 is what is called the trapezoidal rule. And one thing that you're supposed to notice is that under this trapezoidal rule, the area of each stripe is calculated separately. And then the area under the curve is the sum of the areas of all the n trapeziums. So because like when you look at this one here, we go, I don't know where we got the diagram. Yeah, this is what we have. We assume between x0 and x1, this is a trapezium. So we work out that first area first. This is what is going to give us our I1. And we go all the way up to the last trapezium now, which is going to give us our IN. So we find the area of the first trapezium, we add them up to the last one. Then we now, when we add them up, you get the approximation of the integral as required. So any questions on the trapezoidal rule? Any questions on the trapezoidal rule again? Before we move to the next. Are there people in this class?
No question.
Any questions on the trapezoidal rule?
No question.
Are there any questions?
No questions. We can proceed.
We are good, sir.
Yes?
We are good.
Oh, great. So then now, can we very fast then move and look at what happens in the Newton's Cotes formula if n is equals to 2?
Excuse me, sir.
Yes.
I'm requesting that you give us an example on the trapezoidal formula.
Don't worry, we'll get to the example first. Let's move to up to where there's a point where, because I want to get a question where I'm going to work out, because I need to do a comparison on the methods that we shall have derived so that we can say this one is more accurate than the other one, right? Is that okay?
Yes, it's okay.
Okay. So let's look at Newton-Cotes formula for n is equals to 2. And this is called, yes? Asking a question? So we are talking about Newton-Cotes formula for n is equals to 2. And this is sometimes referred to as Simpson's, not Newton's, by the way, Simpson's. No, we start with 1/3 first. It's 1/3 first, then 3/8. Simpson's 1/3 rule for n is equals to 2. Now, suppose we have this curve, y is equals to f of x. Y is equals to f of x is stipulated for, of course, we have x is equals to a plus 2h, a plus 4h, and so on, up to a plus nh, and that is equal to b, passing and this represents like quarter to, it's a quarter to 4. I can stop here, I can do it. Yeah, stop it so that I wait for you. I need to go all the way up to It will be around 4. So, yeah, which course is it? Numerical for engineers. Okay. So suppose we have the curve y is equals to f of x, and we tabulate these points for as in x is equals to a, x is equals to a plus 2h, and so on, up to x is equals to a plus nh, which is the last, the b now. Then these points, they are such like they represent a parabola now, not a straight line anymore. Then we shall have the following, that our integral, this will be equal to the integral a to b, f of x with respect to x, and this is a to a plus 2h, f of x with respect to x, plus the integral a plus 2h to a plus 4h, f of x with respect to x, plus the integral a plus 4h, then a plus 8h, f of x with respect to x plus all the way up to the integral a plus n minus 2h up to a plus nh, f of x with respect to x. It's called that equation 1. So let's have this one as I1 plus I2 plus I3 plus so on plus IN. That's what we have. So in this case, notice the difference between the case where n was equal to 1 and when n is equal to 2. So the x's are in such a way that we have the first term as a, the second term will be a plus 2h, a plus 4h, because n is equal to 2. So then let's see how we can work out this first integral, the second integral, and so on.
Yes,
Then we
sir.
sum up. Once we are able to sum up, then we will come up with the Simpson's 1/3 rule, or Newton-Cotes formula for n is equals to 2.
Excuse me, sir.
Yes.
In the previous slide, is the difference 2 because in the integration you've put in the upper part a plus 2h, a plus 4h, and a plus 8h. Is it supposed to be a plus 6h?
6 now. How does it come to 6?
Because the difference is 2.
No. That's the difference is not twice. N is equals to 2. It's n that is equal to 2. Not that the difference is 2, because you know we have a, let's say for example, the first term is 2. Let's say the first term is 2, right? If the first term, that a is equals to 2. So the second term will be equal to, now if the spacing is say 1, right? So the second term will be 2 plus 2 multiplied by 1. Right?
Yes.
If that's the spacing, then the other one will be 2 plus 4 multiplied by 1. So then the 6 comes here. We have 2, 4, 6. Then the other one will be 2 plus 8 multiplied by 1. So this will be 6, 2 plus, is it 6? This is supposed to be 6, yeah? Because for 6, oh, sorry, it's supposed to be 6. 6h for 3. So that this one becomes 8. So this will be 2, 4, 6, then 8, and so on. So the spacing in this case is 2, 2, 2, 2. Is that okay?
Yes, that's okay.
Yeah. So then in that case, we will have the first integral. This will be a to a plus 2h f of x with respect to x, and this will be 0 to 2 a plus rh dr. This is if we take x to be equal to a plus rh, so that dx is equal to h dr. And of course, the limits in this case will have to change accordingly, so that we have for x is equals to a, r will be equal to 0, and for x is equals to a plus 2h, r will be equal to 2. So the limits will be from 0 to 2. So then we have this I1 will be equal to, we have h, the integral from 0 to 2. Now, when we write out what is under the integrand, in terms of Newton's forward difference interpolating polynomial, we will have this as f of a plus r, the first difference, at that plus r minus 1, 2 factorial, the second difference, at that plus r minus 1, r minus 2, over 3 factorial, the third difference, at that plus, and so on. Of course, that is with respect to dr. Which we can write out as h, y naught, r 0 to 2, that is when you evaluate that at that point, then plus r squared over 2, again 0 to 2, the first difference, plus a half, r power 3 over 3 minus r squared over 2, 0 to 2, the second difference, at that plus, and so on. And we note that as the curve passing through the points, x naught, x1, and so on, is a polynomial of degree 2. Since it's a polynomial of degree 2, hence the differences of order higher than 2 will vanish. This is a polynomial of degree 2, and then the differences higher than those of order 2 will have to go to 0. And therefore, then, in that case, this, the I1 will then be equal to h y1 minus y0 plus 1/3 y2 minus 2 y1 plus y0, then plus 0, and so on. So which will then be equal to h over 3 y0 plus 4 y1 plus y2. Similarly, we will then have, like the same way, I2 will be h over 3 y2 plus 4 y3 plus y4. Then I3 will then be equal to h over 3 y3 plus 4y4 plus y5, and so on, up to in, which will be h over 3 y n minus 2 Is this correct? Plus 4 y n minus 1
I think it should be, the first one should be yn minus 1.
This should be yn minus 1.
Yn minus 1 plus 4 yn plus yn plus.
This should be yn minus 1. Eh?
Yes.
Then the other one is what? Is this n minus 1 then? Or n plus 1?
Plus 4yn.
4yn.
Excuse me, sir.
Hmm.
I thought the reference was yn. So if you're working backwards, we'll be subtracting 1 from the same. Like if our reference is yn as the last one, then it will be y into n minus 2.
When we look at, let's look at this one. H over 3, this is y naught. And then I2, that will be I think there's a problem with that, isn't it?
Yeah, I'm thinking like taking, for example, when we look at I2, if our y4, if our y4 was supposed to be yn, which should be the last one, then you realize with respect to y4, y2 is y into n minus 2.
So then it's supposed to be yn
minus 2 plus 4 yn minus 1, then plus yn.
No, just yn. When do we get to I1? That is when n is equals to 0, isn't it? Then this becomes 4y n minus 1. So this is 3, then 0 minus 1. What's going on with this? Oh.
Yes, I think you're supposed to start from the other side.
Start from where now? Y naught minus plus 4y1 plus y2. So let's look at this one first, the expansion of this. Let's start from this point. Well, we're talking about the limits when x is equals to a, r is 0, and when x is equals to a plus 2h, because we are talking about that, r is equals to 2. So the limits will be from 0 to 2, f of a y naught, 0 to 2, this and the rest that way, all right? Then now, when we come to this, we have twice y naught plus twice y1 minus y naught plus 1/3, y2 plus 2y1 plus y naught. So this will be h over 3. There is 2y naught minus 2y naught, which will be 0. So there is no y naught up to this point, but there is 1/3 y naught here. So h over 3, that y naught, so that is correct. Then here we have 2y1, then plus negative 2/3 y1. That will be 4 over 3 y1. So 4 y1, and that is the case. Now from this one here, then, this one is correct. Up to this point, that's correct, right? Is that okay? Let's do it together, please.
Yes.
Up to that point, it's correct, right?
Yes.
So I2 then, from this one, if
Yes.
we want to work it out, how is it gonna be? We have h over 3. This is y1, come on. I think that's where I made a mistake.
Yes.
Is it y1 or isn't this y1?
Yes, it is.
So this will be 4y2 plus y3. What do you think about that?
Yes, it's okay.
0, 1, 2, because this is y1, so that I3 will be h over 3. Then this becomes y2.
Excuse me, sir.
Yes.
For I1,
Hmm.
we'll be having 2y naught plus, we'll be having 2y1 minus 2y1. So the y1 will disappear.
Which one now? There is, come on, look at this. This is 2y naught plus minus 2y naught, right? So y naught and y naught will disappear. So what is left between here up to that point is positive 2y1, right? Then here we have 1/3 y2 minus 2/3 y1 plus 1/3 y naught. There is no y naught, so h over 3 y1 is correct. So, sorry, y naught, that is correct, right? Now, 2y1 minus 2/3 y1, what is that equal to? That's 1 1/3, which is 4 over 3. So for the y1, we will have y naught will be 1/3. This will be 1/3 y naught plus 4 over 3 y1, then plus 1/3 y2. Are you seeing that? So that's why we factor out this. We have h, we factor out 1/3. So we are left with y naught plus 4y1 plus y2. So then following the same procedure, then I2 will be h over 3 y1 plus 4y2 plus y3. And then I3 now will be h over 3 y2 plus 4 y3, then plus y4. Then can we generalize now for in? This will be equal to what? This will be equal to h over 3. We have y n minus 1, right? Plus 4 y n plus y
minus 2
n plus 1. Yes?
Should be.
Is it n plus 1 or n plus 2?
2.
Can I look at this one? Then I think I can repeat it in our next class, since it's already 4 o'clock. But up to here, I believe it's okay. So these ones, then I work them out before I generalize on this 3 over 8, a quarter, a third, Simpson's a third rule. It's y n minus 2 for y n. Yes, yes. Yes. Why? We will have n times y. That one? Is it that one? Or the next one? The next one. That is what we have. N over 2 or n minus 2? But we are talking about from x is equals to a to x is equals to b. And that's why we have this, you check these limits of integration. This is n. This is when n is equals to 0, n is equals to 1, and so on, up to now n is equals to n, the last term. Because you see, the reason as to why we'll have any terms is that, like, for example, in this case, we are talking about a parabolic representation, which will go up to the third term, isn't it? A polynomial of degree 2, that's a quadratic now. It will have 3 of them. So then what do you mean when you say a polynomial of degree 2? It goes up to x squared, like a constant plus x squared, right? So n in that case is 2. So we'll have 2 terms, or it will be n minus 1. No, it will have any terms, so that's okay. Where I'm getting a problem is where I don't understand why it's not coming to what I want and what I have is, but I gave you some notes. Didn't I give you some notes on this? What is that formula? Y2 anyway, what you can do easily to resolve this puzzle here, you work out this one. We have the limits of integration. So for x is equals to This was the first one. Then the second one, of course, we'll have to look for the limits. And in that case, we have from x is equals to, sorry, we have it here. This is the second one now. This is what we should work out. So I want you to do the integral, this integral, like what we have done for this one. Then you see what we are going to get for I2. Before we generalize for IN, you see what we are going to get for H2. So of course, in that case, you will have to take x is equals to a plus 2h to x is equals to a plus 4h. You get your limits of integration. Then use, of course, the same expansion that we have. Use the same, what you are only going to change are the limits of integration. You'll use the same as what we have there. What you're only going to change for I2 will be the lower limit for integration and the upper limit of integration up to Wednesday next week. Then I'll look at that before I wind up with the Simpson's 3/8 rule. So unless there is a question, I'd beg to stop at that point. Any questions?
Hello.
Yes.
Some
You have been requesting that if you could be able to send the recordings, we help us to follow up. The recordings, we requested that you can send us the recording for the classes.
There is somebody who was supposed to do that. I don't know what happened. I will find out. But I have already sent you notes in advance, isn't it?
Yes, but these ones are more better than what we could find in the notes.
What I sent you is better than what I have. Both of them are my notes.
Okay.
So what I sent to you is summarized. In fact, this one is detailed. Right?
Okay,
so, but still, if you want, I don't know, were we recording today?
No.
No, so we were not recording, I'm sorry. Next time I will record. But try to work out this integral so that when we meet next time, we wind up with this, plus the next one as I finish numerical integration. Any other question?
Just some clarity.
Yes.
So in this integral that we are going to work out,
yes,
what will be our limits?
You will have to change now. You see, like what we have done for the first integral.
Yes.
We are starting from, we have x is equals to a plus RH.
Yes.
Yes, now we will have x is equals to a plus 2h.
Yes.
Then you put r will be equal to what now?
For the second one, we'll be moving from 2 to 4.
So are we doing it, or are we giving it to you as an assignment? So I thought I gave you as an assignment, then we can look at it in our next class.
Oh, okay. Thank you.
Good. Good.
Okay.
Look at it, please. Okay, then goodbye. So we'll try to have the class on Wednesday next week from 8.
Okay, sure.